Hey OS enthusiast, I thought I would go over our notes real quickly about our new section of memory management, and all I'm going to do is point out a few of things that maybe aren't necessarily expanded on in the notes real clearly. So to start off with, this section is about memory management. And what does that mean? That means that the OS handles the computer's memory for a variety of reasons, but the main reason is because processes have to be memory resident in order for them to run. Many times, especially in the past, processes were larger than the amount of memory that a computer had, so not all of the process would fit, and the computer slash OS, its job was to put the parts of the process into memory that were running at the time and keep track of the whole thing. There's a variety of systems that are used for this, and so that's kind of what this system is about. This section is about. Initially, we're just going to talk about the nature of memory and some early systems. We'll work our way into some contiguous memory system management software type things, and then we'll work our way to the modern method, which is paging. Along the way, we'll talk about addressing and address calculations and all that fun stuff. Now, the assignment that we had was just to look over the first few pages of this, and it starts off saying that main memory is essentially just a large array of bytes, which it is. We can think of it as this giant array. The array indices you can think of as the addresses. The first part of the notes talks about basic memory sizes like a bit, a nibble, a byte, and a word and things like that. Oops, that's up here. You can't really read it too well. You can look at your own notes. The one thing it left out was a munch and a crunch. Those are real important. Not really used that much in computer literature that much, but well, in fact, they're not used at all because I just made that part up. So don't worry about that. This next little diagram, we show the process of address generation. Well, that's really pretty basic. A high-level program talks about storage in terms of variables. We don't go, hey, address whatever spot holds this value and add it to the data held in this spot. We say something like x plus y equals z. So we refer to memory positions as variables. Those are called symbolic addresses. When we compile a program, all that gets changed. The compiler builds what's called a symbol table and essentially gives each variable a spot based on its size and type, and each time that variable is referenced, eventually the compiler fills in that location. Compiler sends its object code to a linker, which indeed then does some real important stuff, like ties in common routines. None of us have ever had to really write a print routine, have we? No. We rely on some fella that wrote this routine that went out and finds a bunch of basically sprites with each character in it. The print routine is used by every language, or at least maybe not every language, but most of them. And they're pretty much all the same. So the linker just ties in that code. No reason to keep umpteen versions of that code hanging around. Now, the linker ties in all this stuff. When the program actually runs, we build what's called a program segment, and the loader puts that in memory. Let's see, what's next? We talk about linking types, static and dynamic. Static is awesome, takes up a lot of space because it ties in every routine. Dynamic just makes a link to that routine. Typically we use dynamic because it saves a lot of space. All the little windows on your computer, that code that builds the window is not tied into your code. We just have a link to it. That way we save repeating that code all over the place. I just talked about the symbols and stuff like that. Dang it, what is this shell doing here? Oh, hi. Maybe you should move. Let me say hi again. Okay. That's a little better. So we talk about some of these other addressing types. Symbolic, that is just the variables that I talked about. Relocatable, that means we start from a base address. Absolute means we have the actual physical address. We don't use absolute that much. You probably used it some in what was that? Not computer organization, maybe computer architecture, because when you worked with those small microprocessors, your compiler on your PC builds a piece of hex code and it runs in the same place in the microprocessor every time. So we know that base address, and there's no reason to use relocatable. All routines run in that spot. Although on your PC we use relocatable because when you compile a program, there's no guarantee that it's going to run in the same place every time you run it. And we have a little section on address binding. You can kind of look up that. That's very similar to the relocatable stuff. The confusion in this section comes up with two things. This dynamic loading, and where is that other one? Well, we can compare and contrast dynamic loading, dynamic link libraries, and overlays. Dynamic loading essentially means that each time a routine is called, we have to check to see if it's already in resident in memory. If it's not, we have to move it in there. It puts the responsibility of that job on the programmer. As programmers these days, we don't have to worry about that too much. We don't worry, that's an old thing. As is overlays. Overlays means the programmer splits up the program into chunks that he knows will run in the amount of memory that's there. You have to have pretty good knowledge of the program to do that. There's an example with a compiler. You should look at that example. What we're used to is dynamic link libraries. These are these awesome libraries that the PC has, and most programs use them. I gave an example a little while ago. There's a DLL that builds the window that your program runs in. When you go into your themes and you say, oh, I want this other theme, you're just linking to a DLL that builds a little bit different window. That's how it works. That's how all of the programs switch to that theme. Let's see, what else? The last little thing that I'm going to talk about in this little lesson is this logical versus physical address space. The CPU works in logical space. So it basically assumes that the program entry point is someplace close to the beginning of the program. The variables are probably at location 0 of the program, and then the program entry point is someplace below that. Physical address space is different. So that when that program runs, it gets put at a base address. Every address after that is calculated as a displacement from that base address. This is, now I'm talking only with contiguous memory systems. CPU works in logical land. Depending on what type of memory system we have, whether it's contiguous or paging, we do a translation from a logical address to a physical address. That's the way it goes. Next time, we'll talk a little bit about these types of memory allocation. We'll start off with contiguous. We'll start off with the simplest one, and we'll work our way towards paging. So one more time, let's say hi to our little friend. Hi.